This is lesson 4.4 on exponential functions. And when we talk about an exponential function, it's a function that's going to look something like this, 2 to the x. So we're going to have some constant raised to some variable power. So in an exponential function, once again, just to be very, very clear, the variable is in the exponent. So hopefully that makes sense. For an exponential function, the variable is in the exponent. So contrast this with, say, x squared. So 2 to the x versus x squared. Notice that 2 to the x, our base is constant, and our exponent is variable. Whereas for x squared, our base is variable, and our exponent is constant. When we are dealing with an exponential function, we have a few restrictions on what that base number can be. So that base constant, it has to be positive, and it's also not going to equal 1. The main reason we throw out 1 is because it's just kind of silly. 1 to any power is just going to be 1, so it's not a very interesting function. The reason we throw out the negative ones and 0 is also kind of, it's weird for some values, and for negative values it's especially bad because then we'd be taking the reciprocal of 0, which is undefined. For negative numbers, negative bases are going to be no good because when we take even roots of negative numbers, that's going to lead to an imaginary value, and we don't want to deal with that. So our bases are always going to be between 0 and 1 or bigger than 1, so positive and not equal to 1. So this raises an interesting question. So if we had, thinking back to our example, 2 to the x, we have a good idea of what 2 to the some rational power would be. So if it were 2 to the 3/2 power, we'd raise it to the third power, we take the square root. If for some reason we had a negative in our exponent, we could make that take the reciprocal of our base. But we have never ever talked about what it means if we raise raise a number to an irrational number. So what does 3 to the square root of 2 mean, or what does 2 to the pi mean? The reason we haven't approached that is because we can't really say that. It really doesn't make much sense. But it's something that we've got to approach, that we've got to encounter when we're dealing with these exponential functions. Because if we're allowing x to be anything it wants, then it very well could take on an irrational number. The way that we deal with this is we're going to take all of the rational numbers. Any rational number we put in there, it might seem a little weird, but we can think about what it means. 2 to the 101 over 100. That means we're taking the 100th root of 2 and then raising that number to the 101st power. So any number that we can write as a fraction, we can think of in terms of roots and powers. But again, our irrational numbers don't make any sense. Well, the good news is if you take any irrational number whatsoever, you can find a rational number as close to that irrational number as you want. Think of the smallest number possible, 0.0000001. Do that for a few years, come back, 0.001. We can find an irrational number. For any irrational number, we can find a rational number that is that close to it. So what we're going to do is we're going to take rational numbers that are increasingly closer and closer and closer to an irrational number and use the corresponding values we get back from the exponential function to define what that function is going to equal at the irrational number. So for example, the 2 to the pi example, what we would do is we'd think of, all right, pi we know is 3.1415, blah, 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 blah. We'd say, all right, so what is 2 to the third power? What is 2 to the 3.1 power? 3.1, that is a finite decimal, so we can write it as a fraction, so we can think of it in terms of roots and powers. What is 2 to the 3.14? What is 2 to the 3.141? And so on and so forth. These numbers are going to keep getting closer and closer to a particular number, and that's what we're going to define 2 to the pi power to be. Now that's much more detailed than what we really need to worry about, but it is kind of a weird point of exponential functions that's frequently swept under the rug. So if you're wondering what in the world does it mean, that seems awfully weird, you are correct. That is strange. We don't have a nice little explanation we can tie up with a bow, but this is what we mean by it. We're going to fill in the values that do make sense, and then just fill in the gaps with what would be most reasonable. If this trend continued, what would this value be? Now for the drill problems for this section, again, don't let that bit about irrational numbers scare you. We're not going to have to deal with that head on. It's just, again, I thought it was important for you to know about that. Our drill problems are going to be dealing with the graphs of these. So we've got two options here. So if we are dealing with the graph y equals a to the x, our graph is going to look one of two ways. If the base, if our constant for our exponential function is bigger than 1, then our graph is going to look like it does on the left-hand side. And hopefully this makes sense. If our base is bigger than 1, as x increases, so as x gets larger, a to the x is just going to get huge. It'll get ginormous. So notice here it shoots off as our function shoots up as we move to the right, and as we move to the left, we have a horizontal asymptote at y equals 0. And again, hopefully that makes sense. When we have a negative exponent, we're going to take the reciprocal of this constant and then basically raise it to higher and higher powers. So we're going to have a fractional number raised to higher and higher powers. That's going to get closer and closer to 0. On the other hand, if our base is between 0 and 1, things just flip-flop completely. As x gets very large, a to the x is going to get closer and closer to 0, and as x gets more and more negative, a to the x will just get huge. Now, a very, very common application of exponential functions is looking at what's known as compound interest. So when we make an investment, an investment that's followed using compound interest, what that means is that we invest an initial amount, and after certain set periods of time, maybe monthly, maybe daily, maybe weekly, we're going to accrue interest on this investment. That interest is just going to immediately be reinvested. So the next time interest accrues, it will earn interest, and that interest is immediately added to it. So the next time interest accrues, it also earns interest, so on and so forth, forever and ever and ever. Amen. What we are going to use is we will always use this equation here when we're dealing with compound interest, that where interest is compounded at fixed intervals each year. So if it's accrued monthly, accrued weekly, this would be the formula that we use. We're going to look at a slightly different formula that we use in certain situations later, but a lot of the time this is what we'll use. So we'll see an application problem of this where we need to use this formula. We'll be given most of this information. Most of the time we're going to be given everything except the amount. So what's happening in this formula here is the amount, that's going to be the amount in our investment after a fixed period of time. P, the principal, that's the amount that we initially invest. R is the annual percentage rate. So what is the percentage interest earned from an annual point of view? N is the frequency, how many times per year does interest accrue? And then T is time, generally in years. Now, if we take this formula and we replace a lot of things, if we say, all right, let's let just P be 1, let's let our rate and time be 1, let's only change N, the number of times per year that interest is accrued. Suppose that weekly isn't good enough, daily isn't good enough for us. Having interest accrued every hour, every minute, every second, that's not good enough for us. We really, really, really want to accrue interest continuously. So what we do is if we take this little bit of the of the compound interest formula that we saw before. So this 1 plus 1 over n, all raised to the nth power. If we let n just get huge, we see that we have a little bit of a paradox here. As n gets very big, 1 plus 1 over n is going to go closer and closer to just 1. However, at the same time, we're raising it to a just fantastically large power. So we've kind of got a little bit of a race here. Is 1 plus 1 over n getting close enough to 1 fast enough that it's not going to make the number too big? Or is our exponent getting so big so quickly that it doesn't matter what 1 plus 1 over n does, it's going to get very large? Well, something in the middle happens. If we take this term here and let n get arbitrarily large, what's going to happen is that it's going to get closer and closer to a constant. It's an unusual constant. We use the letter e to denote it. So think of this like pi. E is like pi. It's just a mathematical constant. We do not really need to worry about what it equals. It's approximately 2.71 blah blah blah. 2.7 range, but again, whenever we encounter e, we're almost always going to leave it as e. This e is sometimes called Euler's number. This is one of those unfortunate points in mathematics where there's an Euler's number and an Euler's constant. Two different things, unfortunately. We're not intentionally, mathematicians aren't intentionally trying to be mean and confusing. It's just that, unfortunately, Euler was a really bright guy, and so he did a lot of important stuff. So he's so important. He got two numbers named after him. So this is one of them. So we call this one Euler's number, but most of the time we'll just simply refer to it as E. So if we take this E and plug it back into our compound interest formula, we wind up with this formula here. This is what we call the continuously compounded interest formula. So again, the idea here is, what if we just compound interest? What if our interest accrues just continuously? It accumulates now, it accrues now, it accrues now, it accrues now. So it's always accruing interest. How much money would we have in our account if this money is always accruing interest? And this is the formula that we're going to use to find that. We see basically all the same players from before. Notice the only one missing is n. N doesn't have a role anymore because we are accruing interest continuously. We've basically just replaced n with an extremely large number. So we're going to use both of these formulas in our application problem. We'll look at an investment problem where we want to figure out how much interest or how much will be earned just using standard interest that's accrued monthly or daily, and compare it to how much is earned when interest is accrued continuously. Alright, that's pretty long-winded with the intro, so let's see if I can be a little quicker with the problems. So here we want to sketch the graph of y equals 3 to the x plus 2. So when you first look at this problem, hone in on what is the base of my exponential function. So here it is 3. Since I know that my base is bigger than 1, my graph is going to look something kind of like this. So this is more or less what the graph of y equals 3 to the x would look like. So as I go to the right, I get huge. As I go to the left, I get closer and closer to 0. Now, the function that I'm asked to graph is 3 to the x, y equals 3 to the x plus 2. We have to remember our transformations from a couple units back. This plus 2, since it is outside the function, this is going to be a vertical shift. So it's outside the function, so adding 2, I'm going to go in the positive direction by 2, so I'm going to go up 2. So my graph is going to take this same base function, but shift it up by 2. So it'll look something more like this. Now, to be careful, I would encourage you, go ahead and put a dashed line here just to emphasize that the horizontal asymptote that was formerly y equals 0, we've now moved up to y equals 2. So this right here would be your final answer. You don't need to plot points. You don't need to worry about, oh, is this crossing the y-axis is exactly right. The only thing I would encourage you extra to do here is to go ahead and put in this, this dashed line to show that our horizontal asymptote has changed. If we haven't shifted this vertically, if we did not shift this vertically, don't worry about putting in the dashed line along the x-axis. That's really unnecessary. But if you do have a vertical shift, I'd encourage you to go ahead and do this. Let's look at one more. So sketch the graph of y equals -1/2 to the x power. So again, very first thing, let's go ahead and sketch just kind of the base exponential function. So we have 1/2 to the x power. This time around, since my base is between 0 and 1, my graph is going to look something like this. As I go to the left, my graph gets very large, but as I go to the right, it gets closer and closer to 0. This negative, if we remember from our transformations, or graph transformations, this is going to be a reflection in the vertical direction. So in other words, across the x-axis. So if I take my base graph, reflect it across the x-axis, I'm going to, let's see here, along this way I'll have my horizontal asymptote I got closer and closer to 0 as I go to the right, but now instead of going up, I'm going to go down. So that's my final answer. All we have to do is two things. Check that we get the initial exponential function graph correct. So focus on if your base is bigger than 1 or between 0 and 1. And then just simply apply the transformation that we're doing here. For our drill problems, we're only going to see 1. In general, I would hope that you could use the same techniques that we saw in Unit 2 to handle more complicated graphs. But for the drills, for this test, only anticipate seeing just a single transformation. We'll keep things pretty simple. So here's a little application problem that requires us to use both the compound interest formula at fixed intervals and the continuously compounded interest formula. So in this problem we have Timmy, who's decided to take all of his high school graduation gifts and invest them, and then he plans on withdrawing the total amount after he graduates from college in 4 years. So he has two options. He has one investment would compound interest on a monthly basis at a rate of 4.5%, and another would compound interest continuously at a rate of 4.3%. Now, just a side note, in general, if the rates were the exact same, so if both the monthly and the continuously compounded investment were both 4.5 or both 4.3, it's always going to be a better investment to do it continuously. The more times that interest is accrued, the better, and that seems reasonable. That we would have, if we gain money more frequently, that's generally going to be a better deal for us. Okay, but here it's not apples to apples. We're comparing apples to oranges here. We've got different investment rates, so we need to actually sit down and crunch the numbers. So let's first look at the investment where interest is accruing. It's being compounded monthly. So since this is not continuously compounded interest, the formula that we need to use was the first one that we introduced. So A equals P times 1 plus R over N to the NT. Okay, so our players here, we want to find A. Our P is 1,500. Our R is 4.5%. A silly thing, but don't forget to do it. Write it as a decimal. So 4.5% would be 0.045. Let's see here. Our N, interest is compounded monthly, so it's going to be compounded 12 times per year, and then we're told that he's going to invest this for 4 years, so T will be 4. So putting everything into our formula, 1,500 times 1 plus 0.045 divided by 12 to the 12 times 4, and doing that in our head because we are awesome like that, No, just kidding. Do this in your calculator. We get 1,795.22. Okay, so not a bad investment. All right, now let's compare this with the investment where interest is compounded continuously. So here is where we use what some of us will call the PERT formula. So A equals PE to the RT. So A is what we're finding, P is the same, our R is different, it's 0.043 now, and our T is the same, it's 4. And what's E? E is, remember, just the constant, so our calculator knows what it is. You don't need to remember what the value of E is. So we punch this in, A equals 1,500 times E to the 0.043 times 4. And when we put that into our calculator, we get back 1781.516, so we're going to round that 1 up to 2. Well, which one's the better investment? Well, here, this is more. So clearly, the monthly investment is going to be better. So the monthly account is better. There we go. So we do need to be mindful of both formulas. If these are formulas that we have not encountered before, they really are handy formulas to have on hand, to have memorized. They show up fairly frequently. This in particular, I would especially know. This has quite a few uses in actually several different disciplines, not just in finances, not just in investments. We can actually adapt this formula to work with. It shows up in biology, shows up in physics, all sorts of places this shows up. This primarily shows up, it can show up in many other places, but from my experience, it's used primarily when we're talking about investments that accrue interest at fixed intervals. That's not to say it'll never show up anywhere else, but that's where it shows up most commonly. This, though, really does show up in a lot of different places. It doesn't always look exactly the same way, but at its heart, it is this exact same formula. So these are both important. I would know both of them. When we get closer to test time, we'll talk about what specifically we need to focus on with these.